I told you in this video that we're going to learn how to rank molecules as an R or an S, or if you're using the other code system, a D or an L. So this is the way that you do it. We said that first we have to have a chiral molecule, and we had written a chiral molecule on this slide in the previous video. And I said the chiral molecule has to have 4 different groups, right? Okay, so with these 4 different groups, we're going to have to learn how to rank them. And we do the ranking by nothing more than just the atomic number on the periodic table. That is why I said that you probably need a periodic table around when you do these. So the lower the atomic number, the lower the ranking. That basically means that in this system, here's the center carbon, and we've got chlorine and bromine and oxygen that's directly attached to the carbon. You always go to the one that's directly attached, and then we have hydrogen. All right, well, if I go to the periodic table and I look at the atomic numbers, I'm going to see that atomic number for hydrogen is a 1. So hydrogen, if it's attached to the center carbon, will always be the lowest ranking priority that you will have. All right, so the other 3, we'll get to those in a second, but that's how you begin to rank them. So hydrogen has a 1. Hydrogen has the lowest ranking number out of the group of 4. If you do not have hydrogen, but you have another 4th different group that's attached there, let's say another carbon is there with more groups, or let's say that an iodine is attached there, you still do the same thing. Look at the atomic number, figure out which one has the lowest atomic number, and then that is your lowest ranking one. Now, the reason that I say that is because once you get the lowest ranking one, well, you're going to turn it backward. You're going to turn it away from you. So this hydrogen, I'm just going to put kind of, if I'm doing a 3D model, I'm going to take my hydrogen and I'm just going to shift it backward. And I'm going to point it away from me. And what I have are now 3 groups that I need to focus on. And that group is going to be an OH and a Cl and a Br. Okay? So we've got some distinguishment that we need to do here. And that is a 3D representation. But before I do that, I just want to make sure that you understand how to rank these systems by looking at the 3 groups. So out of these 3, the one with the highest priority, the largest atomic number, is going to be bromine now. So this is going to be my rank number 1. That is the highest priority, and that's where I need to kind of start. The next one would be chlorine, and then the next one would be the oxygen. So again, it's all based on atomic number. All right, so now that I know my 3, I'm then just going to draw kind of like an arrow that points toward them. So it goes from bromine to chlorine, and then chlorine to oxygen, and that's going to be basically a rotation, right? If this was a clock, this would be counterclockwise. It points to the left. And the reason that it points to the left is the reason that we use the S for sinister or the L for levo. So the molecule, the way that I've drawn it here, that is how we determine if it's left-handed or right-handed. And we know from that position that this thing is a left-handed molecule. All right, now what if I switch up these groups? What if I put bromine here, chlorine here, and OH there? Well, I do the same thing. Bromine is going to be the largest priority, and then that points toward chlorine, which is the next priority, which points to oxygen, which is the next priority. All right, this, if it was a clock, would be clockwise. That's the way that a clock normally turns, right? Right-handed. Well, because it goes right-handed, that is why we would label this as an R or a D. Okay? So that's the left-handed and right-handed version of molecules, and that's how you determine them. It's nothing more than just atomic number, and that's it. All right, well, here's the thing. Most of the time when you see these structures, they're going to include all 4. And the way that we'll do that, and I'll just draw the first one just as an example. We're going to have one that points straight up, one that points to the left, one that basically comes out in a wedge towards you, and one that will be a dashed wedge that is representative of pointing away from you. And that's the way that we draw most of these structures. So the one on the dashed wedge, you don't really regard. You leave it off because in this example that would be hydrogen, right? So this is their way of telling you which group goes backward, away from you, that you should not count and that you should not include when you begin ranking the R, S, and the D and the L. So if you see that top, don't let it throw you off. It's just kind of a justification and a confirmation of what goes toward the back, which is your lowest priority group. All right. Now, the next thing that I want to say, a lot of people get confused here because D, L, and R and S, or the D, L, does not represent if the molecule turns light, left-handed or right-handed. Okay? So here's the thing. If you have a chiral molecule, the chiral molecule can be represented with a left-handed or right-handed version. Because of that, because they're chiral, that also means that they rotate light. And if they can rotate light, they will rotate light left-handed or right-handed as well. So in one case, we're talking about left-handed and right-handed hands, and in the other case, we're talking about right-handed and left-handed feet. They have nothing to do with each other, right? So a lot of times in a course or a lot of times in organic, people will get confused. And they will think that a R molecule is right-handed, which means that it will also rotate light right-handed. And that is false. That is not true. So if it goes right-handed, we put a positive here. And if it goes left-handed, we put a negative out in front. So what I'm saying to you is that we can have a right-handed molecule that can rotate light right-handed as well. Or we can have a right-handed molecule that can rotate light left-handed. Both of those are acceptable and both of those are found in a laboratory. Well, I can do the same thing with left-handed. We can have a left-handed molecule that will rotate light right-handed. And we have a left-handed molecule that could rotate light left-handed as well. So these do not have anything to do with each other. The plus and the minus you cannot determine by looking at a structure. And the only way that you can determine what these pluses and minuses are when it concerns how it bends light is through the use of a polarimeter. That is the only way that this thing will work. So you cannot look at a structure that I give you on a quiz or a test and say, well, this is left-handed or right-handed as far as the structure goes, and because of that, we know if it's left-handed or right-handed in the polarimeter. No, you only can determine the direction of the light by putting it into a polarimeter, and that is it. Okay, so you actually have to have the machine, you actually have to analyze the sample, and you have to see how the sample is bending the light, left-handed or right-handed. Now, the Merck or the CRC will typically provide you this information, and the Merck and the CRC are those reference books. So if you've taken 115, which is our quality control class, we've spent a whole, basically, lecture module looking at the Merck and the CRC and other reference sources that are out there for our disposal. So that's one of the ways that you could find out before you actually run it. But you actually are going to have to run these molecules in order to determine the direction of the light and how it bends it. So in the next video, we're going to talk about the polarimeter, and I'm going to give you some background about the polarimeter itself, how does it work, and what happens inside to give us the reading. So the takeaway story here is look at your ranking. And that ranking will help you determine if this molecule is a R version or an S version. Well, in the sugar world, which is what we're using here, we also can use the D and L system. So both of those are the same, dextro and R, or levo and S. It just depends on which one you prefer. So you look at the ranking, you look at how it rotates, counterclockwise or clockwise, and that will tell you if the molecule is left-handed or right-handed, right? That's all that does. When it concerns light, I want you to put a big question mark here, because you cannot determine if that molecule will rotate light left-handed or right-handed, and then you look it up or you actually run it. If the molecule rotates light right-handed, it's a positive. If it rotates light left-handed, it's a negative. And that's the nomenclature system that we use for the polarimeter, or how the molecule will rotate the light. So in the next video, we'll look at the instrumentation.